Welcome back. This section we are going to be looking at ellipses. Last section we looked at circles, which were really basic. All they really have is a radius and a center. There are a lot more moving parts in ellipses. There's going to be a lot of definitions in here. Some of them you actually need to know. Some of them they don't matter as much. But there will be a lot going on when we're working with ellipses. Fun enough, a circle is actually just a special case of an ellipse, but we'll see that later. So, our learning targets for today: I can write the standard equation for an ellipse, and I can graph an ellipse and identify its center, vertices, covertices, and foci. Foci is plural for focus. And see, all these are going to be vocab that we'll get to in a minute. First, what is an ellipse? A lot of people think, well, it's just an oval. Yes, an ellipse is an oval. Not all ovals are ellipses. It's kind of like you can make an oval that doesn't actually fit with the ellipse definition. What is the ellipse definition? An ellipse is the set of all points where the sum of the distances from the point to two fixed points, the foci, is constant. I'll explain that in English in just a second. But remember, the definition for a circle is just the set of all points whose distance from a central point is constant. Well, now we have two distances that we're adding together to be constant. So what are those two distances? What does this mean? Well, if we have an ellipse, these two blue dots are the foci. And again, foci, it's one focus, two foci. Kind of like mongoose. You have one mongoose, two mongai. Anyway, if we pick any random point on the ellipse, let's say this point right here, this distance to this focus plus this distance to this focus will be the same no matter what point we pick. And so if this distance is m and this one is n, m plus n will be a constant for this ellipse. So in this case, it happens to be 10. If we pick a point here, this distance plus this distance is 10. If we pick a point here, this distance plus this distance is 10. And I could tell it was 10 right away because it's actually the distance across the biggest part of the ellipse through the foci. And we go out 5 each way, so that would be 10. Because if this point came down here, we'd have this distance plus this distance, which is everything but this one, which is the same, and so it ends up being this big distance across the ellipse. And that has a name that we'll see in just a second. And so that's what an ellipse is. There's actually quite interesting applications of ellipses. There are some buildings, some rooms specifically, that are called whisper rooms, that are ellipsoids. And an ellipsoid is a three-dimensional deal where this would be a curved top too, because you can't stand in a two-dimensional ellipse. It makes it a room. And what happens in these whisper rooms is if you are standing at a focus and you whisper something, someone can hear you if they're standing at the other focus, but people in between and other places can't. And the reason for that is because any line that you draw from one focus is going to hit the ellipse, and the angle of reflection will take it right to the other focus. So if you draw a line, the angle of reflection will take it here. You draw a line, the angle of reflection will take it right back to the other focus. So all of the sound waves that dissipate when you speak all hit the edge of the room and bounce back to the other focus with a constant distance. And so it's taking all of them, going out all different ways, the exact same time to hit that other spot. And so they can hear you almost as loudly as if you were standing right next to them. And does that have a super practical use? No, but it's just cool. Another not use for an ellipse, but a place that we see them a lot is planetary orbits are elliptical. And not only planetary orbits, but also a lot of comets are also have elliptical orbits. They're not circular orbits, they're ellipses. The sun is at one of the two focal points. My question is, what's at the other focus? I don't know the answer to that. It's probably nothing, but I just think that's a fun question. Now, even though they are elliptical, they are really close to circular, and so the two focus points get closer and closer to the center. In fact, when the two focus points get to the center, they become one point, you actually get a circle. And so it's the further away from each other the foci get, the more ovally it is, and the flatter and flatter, until if you actually extend both of them out to infinity, the ellipse collapses on itself and becomes a straight line. Anyway, so those are a couple applications of where we might see ellipses, and you'll see some more in your in some of the word problems today in your assignment. But they're just kind of fun. Anyway, let's get to some ellipses. Let's get to some of that vocab. So we have two types of ellipses. We have horizontal ellipses, which are the ones that are wider than they are tall, kind of like the one we were just looking at. And we have vertical ellipses, which are the ones that are taller than they are wide. Notice on horizontal ellipses, the foci are horizontal from each other, and vertical ellipses, the foci are vertical from each other. It's very important. We have a center point in each of them. And for these guys, I put the center at 0, 0. It's not always going to be at 0, 0, but for what we're doing right now, we can have it at 0, 0. So these little green dots are the center, and as I mentioned, the blue dots that were already there are the foci. We have vertices, and vertices is just plural for vertex, right? We have one vertex, we have two vertices, kind of like mongoose. We have one mongoose, we have two mongooses. And the vertices are going to be at the end of the longer side. So horizontal, the vertices are going to be horizontal. They're on the same line as the foci. Vertical, the vertices are going to be vertical. Again, on the same line as the foci. And that's just the furthest distance you're going to get away from the center. If we go the other way, we have what are called I forgot. I put major axis in here. The major axis is the line that connects the two vertices. So it connects the vertices and it goes through the foci. So in a horizontal one, it's horizontal. In a vertical one, it's vertical. All right, now if we go the other direction, we have what are called covertices. Now, these are not covertices as in they're sneaking out there. They're covertices as in it's kind of like the other vertices. And that's just the shorter of the two distances. And so horizontal, they're going to be vertical. And vertical, they're going to be horizontal. Notice the only real difference between them is the name. The covertices in horizontal are the vertices in vertical, and vice versa. And the covertices are connected by what's called the minor axis. It just connects the two covertices. And so it's vertical and a horizontal, and horizontal and a vertical. Why would this be important? It could tell you that it has a minor axis length of 4, and so you just have to know that, oh, that means that this distance would be 2, and then you can use that to help make your equation. And again, the vertices and covertices, just knowing which one's which can help get your numbers in the right place for the equation. And speaking of equations, we're going to make them, but first we need some distances. So we have some things. We have the horizontal radius. It's not actually called these aren't radii, but I find it useful to call them the horizontal radius is A, and over here, the horizontal radius is A. The vertical radius we're going to call B. Over here, the vertical radius we call B. The book does this differently. They always put the distance from the center to the vertex as A, and the distance from the center to the covertex as B. And so in vertical, it switched. I think that's stupid, because what it does is it changes all the equations around except it leaves one of them the same, and we can fix that by putting absolute values on that one equation, and we don't need to worry about switching everything else. So personally, I like A to be the horizontal radius, B to be the vertical radius. But again, if you look in the book, it's going to have something different. In reality, these are going to be numbers, and so it's not going to make much of a difference. Anyway, so we have our horizontal radius and vertical radius in both of them. That's A and B. And we also have the distance to the focus. The distance to the focus, we're going to call distance C. And that's going to be a horizontal distance for horizontal, and it's going to be a vertical distance for vertical. So we have three distances here. We have the center to the vertices and covertices, and we have to the focus. Horizontal radius, vertical radius, and focal radius. So now for some equations. If our center is at 0, 0, the equation is going to be x squared over a squared plus y squared over b squared equals 1. X squared over a squared, the horizontal radius, plus y squared over b squared, the vertical radius, equals 1. So I mentioned that an ellipse, or a circle, is just a special case of an ellipse. In a circle, the horizontal and vertical radii are the same. We call it just radius, r squared. So we'd have x squared over r squared plus y squared over r squared equals 1. We multiply by r squared, and so we just have x squared plus y squared equals r squared. And that was our circle equation. Here, that doesn't work out so well because the numbers are different, and so we keep them over here on this side in the denominator. So that's if it's centered at 0, 0. Well, what if we center it somewhere else? The generic point would be hk. We do exactly what we did for circles. The x squared becomes x minus h squared, and the y squared becomes y minus k squared, because all we're really doing is a translation, horizontal h and vertical k. And so we get x minus h squared over a squared plus y minus k squared over b squared still equals 1. So we use a and b. What about the c? How does the c come into it? Because it's not here. Well, c actually comes, we can use Pythagorean theorem. And what happens, so I mentioned that the distance from the focus to a point is, that constant is going to be 2 times a. Well, if we take that point to be the one right up here, we can make two triangles, where the distance from the focus to the covertex back to the focus is 2a. Being that it's directly in the center, that means that this distance is a, which means we can set up Pythagorean theorem, b squared plus c squared equals a squared, which we could solve for c squared, a squared minus b squared equals c squared. And this is the one that the book leaves the same by switching the a's and the b's. Because what happens is, in a vertical, if we go a squared minus b squared, we're going to get a negative number. Do the bigger one minus the smaller one. That's all that happens. The bigger one minus the smaller one. The bigger one minus the smaller one. If you're finding c squared, you can just do absolute values. If you know c and one of these, bigger one minus the smaller one. So now that we have c squared, we can look to see where some of these points are going to be. It's going to be different if the center is at 0, 0 or hk, because we're starting at a different point. We can find the vertices. At 0, 0, we start at 0, we go over a. Well, isn't this the point a comma 0? or negative a comma 0. So we have the 2 points, a comma 0, negative a comma 0, which is plus or minus a comma 0. How about if we start at h comma k? If we start at h comma k and we go over a, didn't we just add a to the horizontal to h? So that's h plus a comma k and h minus a comma k. If we had numbers, let's say we were at 3, 2, and we went over 4, well, that would be 3 plus 4 is 7 comma 2. 3 minus 4 is negative 1 comma 2. And so that's how that works out. And we're going to see that same basic idea for all of them. It's the same as finding your points on a circle. You start with your center, and then you go up, down, over your radius. Same idea. For covertices, instead of going over, we're going to go up or down. And we're going up or down B. So if we start at 0, 0, and we go up B, aren't we at 0, B? Go down B, we're at 0, negative B. So we'd be at 0, comma, plus or minus B. That gets us our 2 points. If we start at HK, we'd have to add or subtract B to K. So we'd have K plus B, K minus B. And then the foci are actually exactly like the vertices, except instead of adding A, we're only going to add C. So we'll have plus or minus C comma 0 and H plus or minus C comma K. For vertical, we're going to do the same thing. We'll have a center at 0, 0 or HK, and we're going to find the same pieces. Now, the vertices and covertices, all that really changed with those is the name, because now this one is further away than that one. The name changed, but how we find it doesn't change. So the vertices of the vertical are going to be the same as the covertices of the horizontal, because we go up or down B. So we have 0 plus or minus B and H comma K plus or minus B. And then the vertices of the horizontal become the covertices of the vertical. Because again, all that changed is the name. We could really call all 4 of them vertices if we wanted to, but that's not how we do it. And then the foci are, again, just like the vertices, except with C. So instead of plus or minus B, we have plus or minus C. And same thing here. Notice the foci for vertical change vertically. It changes the y value, not the x value. So this is a lot of vocab. There's a lot of information on this page, formulas and stuff. We're going to actually see how these work in just a second, but it's a lot of information on this page. So I'd have it down, screenshot it, whatever it is you do. So what are we going to do with these things? One of the things we're going to do is we're going to find the constant sum. Remember, any point, the distance to one focus plus the distance to the other focus is going to be the same no matter where you are. We're going to find what that distance is. And that distance will change depending on the ellipse that we're working with. So let's say we have one focus is negative 5, 0, another focus is 5, 0, and the point is at 0, negative 12. The F1, F2, that's just focus 1, focus 2, because you can't call them both F because they're 2 different points, so we just name them differently. And then P is the point on the circle. So the distance, we're going to have the distance from F1 to P. So distance formula, we're going to have big square root with negative 5 minus 0 squared plus 0 minus negative 12 squared. That's the distance from F1 to P. Then we're going to have to add the distance from F2 to P. 5 minus 0 squared, 0 minus negative 12 squared, all under a big square root. Now we just have to simplify. Negative 5 minus 0 is negative 5 squared is 25. 12 squared is 144. And then 25 plus 144. 25 plus 144 is 169 in both cases. Square root of 169 is 13, and 13 plus 13 is 26. So on this particular ellipse, any point we pick is going to be 26 units to get to each of, or to get to both of the foci, if you added it up. So that's one thing we're going to do with them. And that means that distance across the major axis is 26 units. Another thing we're going to do, and this is what we're going to do more of, the find the constant sum is a fairly minor piece of what we're doing, but we're going to write the equation in standard form. So given some information, like a center is at 0, 0, a vertex is at -9, 0, and a covertex is at 0, 7, we're going to write the equation. So start out with the center. It's at 0, 0, which means we're going to have just x squared and y squared. But they're going to have denominators that we need to figure out. Well, these are going to be the distance to the vertex and distance to the covertex. The vertex, we look at the distance from the center. It's 9 away from the center. It doesn't matter that it's negative because we're going to square it. It's the distance is always a positive number. So at 9 away from the center, and it's in the horizontal direction, which means that underneath the x squared, we're going to get 9 squared. And in the covertex, we went 7 in the y direction, so underneath the y squared, we're going to get 7 squared. And then just square them. 9 squared is 81, 7 squared is 49. We get x squared over 81 plus y squared over 49 equals 1. There's the equation in standard form. Well, when it gives you a vertex and covertex, that's amazingly easy. A lot of times it'll give us a center, a covertex or vertex, and a focus. And so we can still start with what we know. We know the center is 0, 0, and the covertex is 10 away in the x direction. And so we'll have x squared over 10 squared plus y squared over something. We don't know that yet. It'll be the vertex equals 1. Well, we know the focus is 24 away. So we know A and we know C. And then we can use our equation that's almost Pythagorean theorem and plug it in. Notice B is going to be the bigger of the two because it's the vertex. So b squared minus 10 squared equals 24 squared. 10 squared is 100, 24 squared is 576. We can add 100 over, so we get b squared equals 676, which means that b equals 26, but that actually isn't all that important because what goes in the equation? B squared. 676 is right there. In this case, hey, you square a root and it's 26. It's not always an easy square root. So if you had something like b squared equaled 623, well, find the square root's difficult, then you have to square it again. That number just goes here. So 676 goes here. 10 squared is 100. And so we have x squared over 100 plus y squared over 676 equals 1. All right, how about if we have one where the center is not at 0, 0? The center is at -4, 7, a vertex at -4, -3, and a focus at -4, 0. So, first thing, we know our center. We can plug that into the equation. So it'll be x minus -4, x plus 4 squared, and y minus 7 squared. Then we have a squared and b squared equals 1. It's always going to equal 1. And then let's look to see what we have. So the vertex is how far away from the center? Well, the x's aren't changing, which means it's going to be a vertical. To get to the vertex, it's changing. And then 7 to -3, how far is that? That's 10, which, being vertical, means that b equals 10. And the center to the focus, again, x isn't changing, but y is, and it's 7 away. So c equals 7. So from here, we can use the same equation, and the B is the vertex, so we'll have 10 squared minus a squared equals 7 squared, because 10 is going to be the bigger of the two numbers. That's where this is important. And then we can square these guys. 100 minus a squared equals 49. Subtract 100 to get negative a squared equals negative 51, or a squared equals positive 51. And this would be a case where finding a is going to be difficult, 7.1-ish. But we don't need to find a. A squared is what we need for our equation. So 51 will go here, and then b squared, 10 squared is 100, goes here. So we have x plus 4 squared over 51 plus y minus 7 squared over 100. And that's the equation in standard form. So what else are we going to do with these things? We're going to graph them. We're going to graph an ellipse. And to graph an ellipse, you really only need the center, the horizontal radius, and the vertical radius. That's how I was able to graph the one on the board by just looking at the equation. We look at this guy. The center is 0, 0. The horizontal radius is 6. The vertical radius is 9. So we start at 0, 0, go out 6, up and down 9, and then connect it in an elliptical fashion. What really helps in doing these is a bit of graph paper. We graph our center, 0, 0, and then horizontal radius, we're going to go over 6 and over 6 this way. Vertical radius, up 9 and down 9, and then graph it in an elliptical fashion. I understand that not everybody's an artist. It should not look like a diamond or a kite on its side with pointy corners. That doesn't really work. It should look elliptical in general. But that's all it does to do that. If we wanted to find the vertices and covertices, the vertices, we start at 0. We went up 9 and down 9, so we'd have 0, 9, 0, negative 9. Covertices, 6, 0, negative 6, 0. We could find the foci if we want. They're not going to be quite as pleasant. It doesn't work out quite that nice. How about a little harder one? X minus 5 squared plus y plus 2 squared over 16 and 36. So graph paper. First thing I would graph is the center, which is going to be 5 comma negative 2, because remember there's a negative in the equation. So we have the centers at 5 comma negative 2. Now we're going to go over 4 in each direction. If we wanted to find these points, so those ugly looking formulas on the other page, well, we started out at 5 negative 2. We went over 4. It's 9 negative 2. Went backwards 4. That's 1 negative 2. Then we go up 6 and down 6. So 5 negative 2 plus 6 is 5 comma 4. Minus 6 is 5 comma negative 8. Then graph it in an elliptical fashion, and you're done. It's the same way I'd graph a circle, except that we don't go over and up and down the same amount. We go different amounts. Anyway, that's ellipses. Lots of stuff we're working on, but most of what we're actually doing with them isn't hard. It just looks hard because we had a lot of vocab and stuff to deal with first. So I will see you